Welcome to the Deep Dive, the show where we cut through the noise and get straight to the heart of the matter. Today we're kicking off something pretty ambitious, a 12-episode series. It's going to be a journey, really. We'll start with the smallest piece of electricity, the electron, and go all the way up to the huge grids powering, well, everything. So easy to just flip a switch, isn't it? Plug things in. We take electricity for granted. But do we actually truly understand what it is, what's going on under the hood?
And that's exactly what we're diving into today. This first one is all about laying the groundwork. We want to strip away the assumptions, get to the real fundamentals of electricity. Think of it like uncovering the invisible forces, the quantum dance, maybe, that lights up our world. It's pretty amazing stuff happening down at the subatomic level, stuff you'd never guess just by looking around.
I love that, a quantum dance. Because, let's face it, the picture most of us have in our heads is probably, well, pretty basic, maybe a bit cartoony. So let's start right at square one, the absolute bedrock. Everything around us, you, me, this microphone, the air, it's all made of incredibly tiny things called atoms. These are the fundamental building blocks, right?
Exactly right, building blocks of matter. And inside every single atom, you find three main kinds of subatomic particles. First, right in the center, the nucleus, you've got protons. They carry a positive electrical charge. Very important. Also in that nucleus are neutrons. And just like the name suggests, they're neutral, no charge. They kind of help hold the nucleus together. But the real stars for our show today are the electrons. These are the tiny, tiny particles with a negative charge. They exist in the space around the nucleus. And when we talk electricity, the electron is absolutely central. It's the key player, its movement, or even just its potential to move. That's what electricity is all about.
Okay, so positive protons, neutral neutrons packed in the middle, and then the negative electrons buzzing around the outside. And it's interesting, isn't it, that the protons and neutrons make up almost all the weight, the mass of the atom.
Oh, absolutely. It's a huge difference. A proton and a neutron, they each weigh about 1 atomic mass unit in AMU. An electron, it's, less than 1/2000 of that. Incredibly light. So they're crucial for charge and electricity, but mass-wise, they barely register. And actually, that difference also helps explain something you see on the periodic table. You know how the atomic masses aren't always neat whole numbers?
Yeah, like chlorine is 35.5 or something.
Right. That's because most elements exist naturally as a mix of different isotopes. Same element, so same number of protons, but different numbers of neutrons. So the mass on the table is actually an average of those different isotopes, weighted by how common they are. It's a little detail, but shows the complexity.
Fascinating. But yeah, let's zoom back in on those electrons. Because the picture we often get taught in school, that mini solar system model. Nucleus as the sun, electrons as planets in neat orbits. I gather that's, not quite right.
Not quite, no. It's a really useful model for visualizing the idea, don't get me wrong. It helps get the concept across, but down at the quantum level, things get much, much stranger and, frankly, more interesting. An electron isn't just a tiny ball zipping around. Quantum mechanics describes it as a spin-12 particle.
Spin, so it's actually spinning, like a little top.
Good question. But no, not literally spinning in the way we think of it. Spin here means intrinsic angular momentum. It's a fundamental quantum property like charge or mass. It's just part of what an electron is. It's not about physical rotation. Think of it more like an inherent magnetic directionality.
Okay, so it's built in, not something it does, but something it has. What does that spin do?
Right, it's an attribute. And this spin can basically be in one of two states, which we often call up or down, mathematically, +1/2 or -1/2. And here's the kicker. Any charged particle, like our electron, that has this intrinsic spin automatically generates a magnetic field, even without physically rotating. This is, it's fundamental to magnetism and how electricity and magnetism are linked. It's why magnets work, why generators work.
Wow. Okay, so if the little planets model is out, what's the real picture? How do these electrons actually hang out around the nucleus?
It's governed by quantum mechanics, which has rules that are pretty different from our everyday world. Now, the electron is attracted to the positive nucleus by the Coulomb force. That's the basic electric pull between opposite charges. Similar to gravity, but for charge, but it doesn't follow a neat path. Instead, its state is described by something called a wave function within an atomic orbital.
Wave function. Orbital. That sounds abstract.
It is a bit abstract. Think of an orbital less like a path and more like a 3D probability cloud, a fuzzy region of space around the nucleus. It tells you where the electron is most likely to be found if you were to measure it, but it's not in one specific spot until you measure it. It's like Imagine a fan spinning really fast. You see a blur, right? You know the blades are in that blur, but you can't pinpoint one blade. The orbital is kind of like that blur, but even more fundamental, the electron's position is genuinely fuzzy.
Okay, a probability
Yeah.
cloud. Mind-bending. But then if the negative electron is attracted to the positive nucleus, why doesn't it just spiral in, crash? What keeps atoms stable?
That's one of the key insights of quantum mechanics. If they were just classical particles, they would spiral in. Matter wouldn't exist as we know it. The reason they don't is because electrons can only exist in specific discrete energy levels within those orbitals. Think of it like steps on a ladder. You can stand on rung 1 or rung 2, but not halfway between. These allowed levels are defined by quantum numbers, sort of like an electron's address within the atom, specifying its energy, the shape of its orbital, and its spin. And the stability comes from wave-particle duality. Electrons act like both particles and waves. Imagine a guitar string. When you pluck it, it vibrates, but only certain wavelengths fit perfectly between the fixed ends to create a stable sound, a standing wave. It's similar for an electron's wave nature around the nucleus. Only certain standing wave patterns can fit stably. These correspond to the allowed orbitals and energy levels. To move between levels, an electron has to absorb or emit a precise packet of energy, a quantum. It can't just gradually slide down.
So the wave nature is what forces it into these stable energy levels.
Amazing. And there's another rule about how electrons fill these levels, right? Something about not crowding.
Absolutely. Crucial rule. It's the Pauli exclusion principle, named after Wolfgang Pauli. It states that no two electrons within the same atom can have the exact same set of quantum numbers. They can't be in the identical quantum state. Practically speaking, this means each orbital, defined by its energy and shape, can hold a maximum of 2 electrons. And if it holds 2, those 2 electrons must have opposite spins, one spin up, one spin down. This principle is, well, it's why chemistry exists. It forces electrons to fill up orbitals in a specific order, from lower energy to higher energy. This arrangement dictates how atoms interact, how they bond, what molecules form. It builds the entire structure of the periodic table and all the diversity of matter. Without it, all electrons would just pile into the lowest energy state, and every atom would be boringly similar. No complex structures, no life. That's incredible. Such a simple-sounding rule with such massive consequences. Okay, so we've got these fundamental particles, electrons, behaving in these very specific quantum ways. Let's connect this back to experiences we all have. That shock, that little zap when you touch a metal doorknob after walking on carpet.
Yeah.
Or maybe pulling clothes apart from the dryer and hearing them crackle. That's electricity too, isn't it? But a different kind.
Yes, that's our first type. Static electricity. It's a great place to start because it's so relatable. Static electricity happens when there's an imbalance of charge. Electrons build up in one place or stripped away from another. So when you rub that balloon on your hair, you're literally scraping electrons off your hair and onto the balloon's surface. Your hair ends up with a net positive charge, the balloon with a net negative charge. That imbalance creates the electrostatic force attraction or repulsion, making your hair stand up or the balloon stick to the wall. And think about lightning. That's static electricity on an absolutely epic scale. Inside storm clouds, collisions between ice particles and water droplets cause a massive separation of charge, usually negative at the bottom, positive at the top. When the difference between the cloud and the ground, or another cloud, gets big enough, the air itself breaks down as an insulator. And zap! A gigantic discharge of electrons leaps across the gap to neutralize the imbalance, a natural, powerful example.
And the word electricity itself actually comes from observing these static effects, way back when.
It does. It's got a neat history. Back in 1600, William Gilbert, an English scientist, coined the term electrica. He based it on the Greek word electron, which means amber. The ancient Greeks knew that rubbed amber attracted light things like feathers. Gilbert studied this properly and figured something invisible, maybe particles he called an effluvium, must be causing it. The word electricity, as we use it, came a bit later from Sir Thomas Browne in 1646. And then people like Benjamin Franklin really pushed things forward, thinking about electric fluid and positive and negative charges. It all started with static observations.
Okay, so static is about charge buildup and then a sudden release, a temporary thing. But the electricity powering this studio, my lamp, your computer, that's constant. It's flowing. That's current electricity. How is that different?
The key difference is right there in the word flow. Current electricity is about the continuous, sustained movement of electrons through a material. It's not just a quick buildup and discharge, it's a steady stream. We define current as the rate of charge flow, how much charge, how many electrons are passing a point per second. So static is like a dam bursting, a sudden rush. Current is like a river flowing steadily along its channel.
A river of electrons. I like that.
Yeah.
And there's that convention about which way the river flows, right? That could be confusing. Positive to negative or negative to positive.
Ah, yes. The classic convention confusion, it comes from history. Before electrons were discovered, scientists like Franklin guessed that the electric fluid was positive and flowed from positive to negative. So, conventional current, used a lot in electrical engineering, still shows arrows going from plus to but we now know it's the negatively charged electrons that actually move in most conductors, flowing away from the negative terminal and towards the positive one. That's called electronic current, often used in electronic engineering. The really important thing to remember is it's just a sign convention. The amount of current, the physics, it all works out the same whichever way you draw the arrow as long as you're consistent. It describes the same phenomenon.
Got it. Consistency is key. And this charge itself, the negative property of the electron, the positive property of the proton, can we make more charge or destroy it?
Absolutely not. And that's underpinned by one of the most fundamental laws in all of physics, the law of conservation of charge. It states very clearly, charge cannot be created or destroyed, ever. It can only be transferred from one object to another or moved from one place to another. In any closed system, the total net amount of charge always remains constant.
No charge magic. It's always accounted for.
Exactly. And this isn't just some abstract theory. It's vital for practical engineering. Think about a capacitor storing charge. This law guarantees that the charge you put in is the charge you get out, minus tiny losses perhaps. It makes devices predictable. Or consider ionization when an atom loses or gains an electron. It becomes an ion, it's charged. But the electron didn't disappear, it just went somewhere else. The total charge in the system is conserved. This reliability is why electricity is so useful.
Okay, so we have electrons, they carry charge which is conserved, and their flow is current. Now, how do we control that flow? Because clearly electricity doesn't flow through everything equally. Some materials are like open doors, others are like solid walls.
That's the crucial next piece, materials. You're spot on, they behave very differently. Imagine electrons trying to get through different substances. Some are like wide, empty highways, others are like impenetrable barriers, and some are like adjustable gates.
Let's start with the highways, the materials that let electrons cruise through easily.
Those are conductors. Mostly metals, think copper, silver, gold, aluminum. Their key feature is having free electrons. These are usually the outermost electrons of the atoms, and they aren't strongly tied to any single atom. Instead, they form a kind of sea of electrons that can move easily throughout the whole material. So if you apply an electrical push, a voltage, across a conductor, these free electrons readily flow, creating a current with very little resistance. That's why copper wire is everywhere. It's a great electron highway.
Makes sense. And the opposite, the brick walls, the materials that stop electrons dead.
Those are insulators. Things like rubber, glass, plastic, dry air, porcelain. In these materials, the electrons are tightly bound to their atoms. They're locked in place, essentially. There are practically no free electrons available to move and carry a current. So they offer huge resistance to electricity flow. And insulators are incredibly important for safety. The plastic coating on wires, the ceramic knobs on power lines, they stop the current from going where we don't want it, preventing shocks and short circuits.
Okay, conductors let it flow, insulators block it. But you mentioned a third type, the adjustable gates. That sounds really interesting.
Ah, yes. The semiconductors. These are the materials that have literally changed the world. Silicon is the most famous example. Their ability to conduct electricity is naturally somewhere between conductors and insulators. Not great, not terrible. But the magical part is that we can engineer their conductivity. We can tweak it precisely. By adding tiny amounts of specific impurities, a process called doping, we can either create extra free electrons, making it N-type, or create holes where electrons are missing, which act like positive charge carriers, making it P-type. This control allows us to build devices that can switch electricity on and off or amplify it with incredible precision. This makes semiconductors the absolute foundation of modern electronics. Transistors, diodes, integrated circuits, computer chips, solar cells, all of it relies on our ability to precisely manipulate electron flow in semiconductors. It's where the real control comes in, enabling all our digital tech.
It's truly amazing that controlling tiny electrons in silicon leads to smartphones and everything else. Let's quickly tie this back to some real-world things people see.
Good idea. We mentioned lightning nature's spectacular uncontrolled display of static discharge. Raw electrical power.
And the much smaller, but way more frequent, static shock from a doorknob.
Exactly. That little zap is the same physics, just scaled way down. Friction builds up charge on your body. touch the metal conductor, and the electrons jump across the tiny air gap to equalize the charge imbalance. It's a direct, personal experience of electrons moving to find equilibrium. Everyday physics in action.
So wrapping up this first deep dive, we've really gone down to the foundations. We've looked inside the atom at the electron, this tiny particle carrying negative charge, which is the heart of electricity. We've seen how its behavior, either building up static or flowing continuously, current, defines what we experience as electricity, and how different materials act as highways, conductors, roadblocks, insulators, or sophisticated gate semiconductors for this electron flow.
And understanding these basics, the electron's weird quantum nature, its charge, the conservation law, how it moves or doesn't move in materials, it's the essential first step. Everything else we'll talk about in this series, all the complex technology that powers our world, it all builds on these fundamental principles. We've really just scratched the surface today of how this invisible force governs so much.
And we are definitely going to keep scratching. Join us next time for episode 2. We'll be tackling the big 3 measurable concepts: voltage, current, and resistance. Getting a grip on those is key to understanding how electrical circuits actually work. You won't want to miss that. And here's something to chew on until then. If electrons are both particles and waves, forming these stable standing wave patterns in atoms, what does that tell us about the underlying fabric of reality itself? How much more is hidden in the quantum rules that allow us to harness this force, turning something invisible into, well, everything from tiny phone screens to entire cityscapes?